So it's my great pleasure to introduce Bernd Sturmfels again. Now, luckily, I get to go off after Lisa, who did all the great introductions. So I don't really actually have much to add other than I really enjoyed Bernd's talk yesterday, and I expect that today's talk will be equally exciting. And the title of today's talk is Gram Matrices for Isotropic Vectors.
Yeah, thank you very, very much. So there's a paper with this title, and the co-authors is Yassine, who is a postdoc at Caltech, and Swala, who is a graduate student in Berkeley. Oh, you hear more about her. Universe Plus, this big thing, is the name of the grant I have with the physicists, and I'll tell you more about this. And plus stands for positive geometry. Now, the way this talk will go, so yesterday was meant to be understandable. Right? Yesterday, everything was, so today, so today the first half I think will be comforting. I mean, it will be a territory that's happy and familiar to commutative algebraists who like matrices and determinants, and then the second half will be harder. The second half I'll actually tell you about physics and the motivation for this work. And I'm going to make good on the promise that this is sort of commutative algebra in the sciences. So you don't need to understand the science, the physics that's behind it, but I just want to give you the spirit, how you can take something from the outside world and turn it into commutative algebra, right? So there was some stuff that the cosmologists did, and we turned it into ideals and so on and so on. Okay, but let me start with the puzzle. So again, that's for the undergraduate students over there. So let's look at a 4x4 matrix, and it's symmetric. It's a symmetric matrix, and I want it to have zeros on the diagonal. Okay, so there are 6 unknown parameters, A, B, C, D, E, and F. And the puzzle is to find describe all the matrices like this that have rank 2. Okay, that's the goal, right? Now, it's easy to make matrices of rank 0, right? You just put all the, they can't have rank 1, right? As soon as one entry is non-zero, this has to have rank at least 2, and I'm interested in all the matrices of rank exactly 2, and we'll get back to this later. This is from the grant with the physicists, so it's called positive geometry, that's the middle, in particle physics, that's the left, and cosmology, that's the right. So this is a scattering process. So particle physics is a experimental science. People actually make expensive experiments, and they scatter stuff. And cosmology is an observational science. So you can't really make experiments in the sky so easily. And this represents a 3-point function in cosmology, but we'll get back to this in the incomprehensible part of this talk. So I'll start with the understandable talk. So suppose you have 6 vectors in an r-dimensional space, maybe real, and I'm going to call these vectors P1, W1 up to W3, and I would like these vectors to be isotropic and pairwise isotropic. So there's some quadratic form in R to the R given by a symmetric matrix, some dot product, but not the usual dot product, but some quadratic form. And I would like to have that every vector dots to 0 with itself, and then Pi with Wi also dots to 0. Right? So these are isotropic vectors, and for every I want them to be pairwise isotropic. Okay, and Q is some fixed symmetric R by R matrix. Now, in physics, this is our favorite matrix, right? We take this, so if the -1 were a +1, then this would be the usual dot product, but we have one -1, right? So the space around it is a 4-dimensional space, or 3 space dimensions, 1 time dimension, and here we have this -1 for the time dimension. Now, in the story that's coming later, there would be 3 massless particles, and each particle now has 2 vectors associated to it. So Pi is the so-called momentum vector, and Wi is the polarization vector. And if these are massless particles, they will satisfy these isotropic constraints. Now, what I'm going to do in this lecture, I'm going to go through 4 levels of increasing physical interest, right? So, and these are sort of coordinate systems. And the first 2 you'll be happy with, and the last 2 you'll be confused by. Okay, that's the plan. Okay. Well, the first coordinate system are just the coordinates of Pi and Wi, right? These are vectors, they have coordinates, and maybe you write them down or you measure them, right? But they are not so interesting, right? Because in physics and in geometry, we're interested in invariant quantities, right? We're interested in the invariance of the relevant quantities, the relevant Q group, and the group here is the special orthogonal group, SOR, with respect to this quadratic form, right? So these are R by R invertible matrices that preserve the quadratic form, okay? Now, what are the invariants? Well, they are these dot products, and these are the entries of the Gram matrix. So the Gram matrix records pairwise inner products with respect to my quadratic form. So this is written here in matrix notation. So here in the left matrix, P1, W1, I write my vectors. I have these momentum vectors, polarization. I write them as rows of the matrix. So this is a 6 by R matrix. Then here in the middle, I have my R by R symmetric matrix, and here I have the transpose. That's an R by 6. Okay, so this is a 6 by 6 matrix. Now, remember, I assume that these Pi and Wi dot to 0 with them. So my isotropic assumptions is that I have these 0 blocks on the diagonal. So this hypothesis here said I have these entries. And these entries are, that's my second coordinate system. And those are better coordinates because they are invariant, right? So if I have these W's and R's and I rotate them around, okay, Megumi, what's the rank of this matrix? People in the last row get a question, right? So what do you think is, so X is a 6 by 6 matrix. In your opinion, what's the rank of this matrix? Depends, that absolutely depends on the P's and W's. Very good, very good. Okay, I would like to say it's at most R, and if these are random enough, it's exactly R, right? So the exercise was also for the people who walk in right now, okay? So here is you have a matrix, you have a 6 by R matrix times an R by R matrix times an R by 6 matrix, then this matrix has rank at most R, okay? And R is less than 6. Very good. So the Gram, this is also called the Gram matrix. Now in algebra, which is what you're in, we would form a polynomial ring in these variables, xij, and the requirement that the rank is at most R, we'd say we make the R plus 1 minors vanish, right? So I look in the 12-dimensional space with these coordinates xij, and I ask the question, what's the variety in this 12-dimensional affine space, or maybe 11-dimensional projective space? And the answer is obvious in this audience. You ask Berkeley 2, or some people in Germany now like to use Oscar. So use your favorite Gröbner-based computer system, and you ask that computer system. Okay. Now, before I say something about the answer, so here's sort of a psychological comment. So in applied algebra, for many, many years, I was often inspired by optimization and statistics. And if you see a symmetric matrix in optimization or statistics, more often than not, it's positive definite. It's real and positive. Now, positive definite says all the action, or most of the action, is along the diagonal. Right? The diagonal has a lot of action. Right? Now, this is the opposite. Right? In this physical situation, along the diagonal, you have zeros or 0 blocks. So psychologically, this is sort of the opposite, from the way we think about positive definite matrices, say in semi-definite programming, Gaussian random variables, and so on. Okay, so we type this into Macaulay 2, so let's try it out, right? So using Gröbner basis, we explore 6 determinantal varieties, 1 for every rank. So they're nested, right? So I'm going to go now by increasing rank. And yes, you can do this at home, right? So start with R equals 0, right? So then my ideal is generated by the 1 by 1 minor. So those are the 12 variables. So in this case, the variety is the origin. The only solution is a 0 matrix, and this is an irreducible variety of dimension 0. Okay, that was easy. Now let's do rank 1. So we take the 2 by 2 minor. So It turns out it's still just the origin. The only solution is just the origin, but now it's an origin with multiplicity 13. It's a fat point at the origin. Okay, let's go up to rank 2. Rank 2, remember, that was the quiz. Hasn't been forgotten. Okay, so for rank 2, we take the 3×3 minors. And in this case, the affine variety has dimension 5. So it's a 5-dimensional variety in 12-dimensional space. But it has 3 irreducible components. And also, it's not radical, not convex. It has embedded components, right? So it has 7 associated primes, 3 minimal, 4 embedded. Okay. Now, R equals 3 is interesting. So this is a secretly toric variety. So it turns out that the radical of this ideal is a toric ideal. It's a nice toric variety. But the ideal itself is not prime. It's not a binomial ideal. So ideal here is primary. It's not radical, but it's a 6-dimensional affine toric variety. Okay, let's try R equals 4. So for R equals 4, it's interesting. So it's radical, but it's actually not prime. Right? So now you get a 9-dimensional variety, and it has 4 components. So it had 4 irreducible components, and one of them I like better than the others. And I'll come back. That has to do with the cosmology, right? So there are 4 components. And finally, last but not least, if R is 5, well, there's just one equation. It's a determinant of my 6×6 matrix. It's an irreducible polynomial, so a principal prime ideal, and the variety is a hypersurface, 11 dimensional. Okay. So this slide shows that there's a wide range of different behaviors that you can have. When I show this slide to my physics friends, I'm saying that there's this field in math called commutative algebra, and it's full of blue adjectives. So, and it's helpful to, it's helpful to study these adjectives when you want to speak about ranks of matrices. Okay. Any questions? So all of this, remember, all of this is the very understandable part of this lecture. So yes.
The 4, R equals 4, is it mixed?
Yes, they all, in this example, they all have the same dimension. Yes, in this example.
There is no clear algebraic way to distinguish.
There is a clear algebra, so there will be theorems in this talk, right? So yes, so we'll get there.
Okay.
But the example clear, right? So this you can do yourself, right? You can, but again, it's sort of psychological. I mean, there's a lot of literature. Many people in Geneva and elsewhere study, determinantal ideals, matrix Schubert, ladder determinantal ideals. But apparently there is no literature on this case, right? That where you put blocks of zeros among the main diagonal. And I think it just sort of hasn't come up a lot. But these are isotropic vectors. Okay, so let me give you the general definition. So we're going to look at fixed integers n and k, positive. We're looking at symmetric matrices of size kn. And I will put 0 blocks of size k along the diagonal. So here's the formalism. So I have a symmetric matrix, variables are xij, and then this third line says exactly that. There are 0 blocks, k by k blocks, okay? So we form the polynomial ring and all of these variables, for simplicity, made with complex coefficients. And then the number of variables, well, is this binomial coefficients. These are all the entries in a symmetric matrix minus the number of entries I've set to 0. So this is polynomial ring in capital M variables. And I'm going to use this notation, V, K, N, R, for the variety of matrices in this affine space of rank at most R, and corresponding ideal with R plus 1 minus, right? So again, the parameters, so K is the size of the 0 blocks, N is the number of blocks, and R is the rank, the specified rank. Yeah, and Megumi, I'm picking the rank. It's not the vectors. It's not, I don't let the particles pick I pick the rank, okay? Okay, very good. So this is this variety, okay? So quiz, right? What's V233, right? Just to make sure we're on the same page, right? So this is a 6 by 6 matrices that have 3 0 blocks of size 2 by 2, and the rank I choose to be 3. Okay, and this was one of the examples that we had on the previous slide. Okay, so Elisa asked for theorems. So here's the first theorem, right? So is this ever irreducible? Yes, it is. It's always irreducible in the high rank regime. So the high rank regime is the rank is bigger than 2k plus 1, and k is the size of the blocks. So if R is at least 2k plus 1, then the variety is irreducible of this dimension. So this number, n times this thing minus R choose 2. R choose 2 is also the dimension of the orthogonal group here. And the minors generate the prime ideal. Not that the variety is irreducible, it's a prime ideal, and it's Cohn-Macaulay. So it has the expected codimension. And again, commutative algebra is a very useful subject. It's the study of blue adjectives. Okay, so that's the first theorem. So it says if, so now in our example, remember in our example, k was 2, and so this is 5. Right? So for any size n, for any number of particles, if k is at least 5, then you have prime ideals, but below that you have this slightly erratic behavior that we saw in the example. Yes, it's an if and only if. We'll come to the converse in a moment. Okay, let's do another example. So even k equals 1 is interesting. Right? So k equals 1 says 1 by 1 block. So I just put zeros on the diagonal. That's it, right? So here X is a symmetric n by n matrix with zeros on the diagonal. So we're looking at V, 1, and R. So high rank regime here means R is at least 3. So if R is 3 or more, it's prime and irreducible. For R equals 3, this is our good old friend from yesterday. That's just the squared Grassmannian. So I hope many of you have spoken to Hannah over there about the squared Grassmannian. For R equals 0 and 1, it's just the origin, but the interesting case is R equals 2, and that was the puzzle. So the puzzle that you can give to all your linear algebra students is what are the matrices here of rank 2, or in the language of this talk, what's the variety V, 1, 4, 2? Well, okay, yes, you put this into Macaulay 2, and it's a radical ideal, and it's the intersection of these 7 primes. Right? So there are 4 monomial primes of codimension 3, and then there are 3 other primes, a little bit of a toric equation. Right? So in general, for 1 by 1 blocks, so this variety, in the interesting case, so this is the variety for 1 and 4, it has 2 to the n minus 1, minus 1 irreducible, that's 7, that many irreducible components. They all have the same dimension, unmixed. The codimension is n minus 1, choose 2. And if you add up the degrees, you get 2n minus 3, choose n minus 2. That's what you expect. And so in my example here, you take 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 2, and that's 10. Oops. Yeah, and the minors, the 3 by 3 minors generate a radical ideal, but it has these interesting components, right? So for your undergrad linear algebra students, right? So the way you can make this matrix have rank 2 is you delete everything outside a given row and column. Right? So you only, if only C, E, F survive, if A, B, and D are 0, right, then this has rank 2. And the other thing that you can do is you can make a little 2 by 2 block of rank 1, but you set the other variables to 0. Right? Those are the possible ways. Okay, yeah, is there a converse? Yes, there's a converse. There's a stronger statement. So here's another formulation. So in general, for every R and every K, we have a dimension formula. And it goes like this. So let me write L for R over 2 rounded down. Okay, so again, N is the number of blocks. the number of particles at CERN, or the number of fields in cosmology, that's N. K is the size of the blocks, R is the specified rank, I choose that, and then L is half of the rank. Okay. Well, then the dimension, there's the low rank regime and the high rank regime. So in the high rank regime, which I here take to be R is greater or equal to K minus 1, and it's this number. But then it's a bit more complicated in the low rank regime, it's this number. So this only depends on R, K, and N, the dimension formula. In the second case, it's Cohn-Macaulay, but what's kind of an interesting thing is that these regimes have an overlap, right? So the way I wrote it is that the low rank regime and the high rank regime overlap in 4 numbers, namely these numbers from 2k minus 1 up to 2k plus 1. And this is in the paper. If you like binomial coefficients and you really, really don't like the rest of the talk, you can check that these two numbers, so it's a little exercise for these values, these are the same numbers. Okay. Another theorem, it's a characterization. So when is it irreducible? So here's an if and only if. So the variety for K and R is irreducible if and only if a disjunction either R is odd, it's always irreducible if R is odd, or R is at least 2k minus 1, or at least 2k plus 1. Right? Now in the even case, when that fails, so if R is even and in the low rank, so if R is even and between 4 and 2k, the number of irreducible components is 2 to the n minus 1. But in the quiz case, where R is 2, we lose one component. It's a 2 to the n minus 1 minus 1. Okay, so we yes, question?
Are these components naturally labeled by subsets?
Yes, they are labeled by subsets. Okay, so those are some results. Now, of course, theorems are for those who can't compute, right? So then you have to do a little bit of computations, right? So some data. So we computed lots of examples. So here is R, the specified rank. Then here K is a 2, 2, 3, and then Kn is this pair, right? And so we're computing the, so we have explicit parameterizations of the irreducible components, but this is the first one. The first number is the dimension. So a variety walks into the door, dimension, degree, and then the number of ideal generators. So in each case, this is generated by the R plus 1 minors, and I just count how many linearly independent generators there are. And okay, yeah, so these are some range. So for example, if you take a 10 by 10 matrix with vanishing, with 0 to 2 by 2 0 blocks, and you specify the rank to be 5, right? Then the degree of this variety, it's a 25-dimensional variety, and the degree is 151,008. And it's generated by 13,866 sticks. Right? So fill this table. Many, many. Okay, so we understand this fairly well. And again, maybe some of the commutative algebraists have not yet used numerical algebraic geometry. The time has come on Monday, right? So the time. So if you want to know bigger examples, like, so this degree you will not get with Macaulay 2. Right? If you type in these 6 by 6 minors and you say degree, it will not terminate. Okay. Very good. So you can see we covered 9 slides. And this is the end of the happy, understandable talk. So this is part of the talk. So this would be a very good moment to ask questions. Yes, Hannah. No. It's actually interesting. Even in the quiz case, they do not form a Gröbner basis. So here, if you part of the exercise, right? So look at the 3 by 3 minors here. Even in this case, they do not form a Gröbner basis under no terms. There does not exist any term order which makes this a Gröbner basis. Yes, question.
The idea of saturated?
These are, I think the answer is yes. I think we understand enough that they're always saturated. Well, except in the serial, in this case where it's just the origin, yes. Are they generators of S? Yes, I think so. Yes, so that would be interesting to look at this from the representation theoretic point of view. Yeah, we haven't done that, but in fact, in some of the proofs, we're using quite a bit of stuff about orthogonal Grassmannians. So there's a bit of representation theory under the hood, but we haven't specifically, explored this question, right? So what is this as a module? How does this split up into irreducible representations? And this morning we had a little study session as what these irreducible representations are. And so this would be very interesting to look at this from the point of view of representation theory and algebraic combinatorics. Yes. I don't know. We haven't studied it. So anyway, it's up for grabs. Right? So we wrote this paper. It was motivated by something. And these are fairly clean statements, right? Although you can see there's sort of this border between erratic behavior and then and for high rank, it gets a little better. Okay? Yes, one more question, Sean. Yeah, so I now have to go back. That's a very good question. Why is this column symmetric?
Can you repeat the question?
The question was, why are some of the columns symmetric for the number of generators, right? Is that a very good question? I think we can probably answer this, but I can't on the spot at this moment. Yeah. Well, I think, okay, you're in a matrix, right? And you have like, okay, let's say you have a matrix. Say you have a 5 by 5 matrix. I want to count 2 by 2 minors, or maybe 4 by 4 minors. Right? That's the same, right? Now, of course, if they're completely independent, but unless there's some zero entries, right, there could be linear relations. So if the zeros don't mess you up too much, right, then 2 by 2 minors and 4 by 4 minors are counted by the same product of binomial coefficients. Did I say this right? Please check me, okay? I think that's true. No, 5 choose 3, I'm sorry, 5 choose 3 equals 5 choose 2. So counting 3 by 3 minors is the same as counting 2 by 2 minors. But the vector spaces they span might have the same dimension or not, depending how many entries I knock out by zeros. Anyway, this is meant to be very happy, and you have lots of blue, you know even more blue adjectives than I do, right? And you can apply them all to this situation. Now, the project started in August. Our grant started in August. So again, the grant is called Positive Geometry in Particle Physics and Cosmology, and we had our first annual meeting. And so the project started in June, and we had the first official meeting in August. And the cosmologist on the team is Daniel Baumann from Amsterdam. And he had just put out this article, like literally 2 weeks before. Now, here's another thing about physicists. So mathematicians, we take our time. We have profound, deep results. It takes us 2 years to referee a paper, and not so in physics, okay? Anyway, so they came out with this paper called A New Twist on Spinning ADS Correlators, whatever these things are. DS is de Sitter and ADS is anti-de Sitter. So your differential geometry friends in your department, they know what ADS is. And this we start discussing, and this led to the paper. Okay? And in the beginning, we were going to work together, but I failed a little bit of convincing them of the utility of blue adjectives, so we decided just do the math first. But hopefully, we're going to get back. So how do we get to this? Well, I told you there are 4 levels, right? So there's the coordinates themselves of the P's and the W's. Then the next level were the entries of the Gram matrix, the Xij, over which we spoke the last 25 minutes. And then there's 2 more levels to come. Okay, so I don't know about this okay. Okay, maybe they can fix it. Hello. Okay, so maybe somebody can click on okay. Oh. On the screen? Okay, I'll let you, okay, maybe. Try. Ah, okay.
Yeah.
Ah. Okay. So there's something called conformal field theory. And so the conformal group is a big group. So SON or SOR is a small group. The group of conformal transformation is some big group, right? But we're really interested in conformal invariants. And there's something that takes the big group and replaces them by the small group, and that's called the embedding space formalism. And what it does, if you have vectors in RD, it tags on two coordinates and makes vectors in R to the 2D. Okay? Now, in this bigger space, you take the Lorentz cone. So the Lorentz cone is the cone where the dot product with itself is equal to 0. Right? So this is this funny inner product, Lorentzian inner product. So not only physicists like Lorentzian polynomials, everybody, combinatorialists these days like Lorentzian polynomials. Right? Everybody likes Juniha and Lorentzian. So this is called the universal speed limit. So the universal speed limit says there's the light cone, and you're not allowed to leave the light cone. You have to obey. You cannot be faster than the speed of light. You have to stay in the Lorentz cone. But this has two parts. It has the future part and the past, right? And you have to stay inside, okay? So what you're going to do is you think about this Lorentz cone as a projective variety. So this is a quadric in a projective space of dimension d plus 1. And that is, of course, birational to affine space of dimension d, okay? So the embedding space formalism says I take affine space of dimension d, and I map it to the d-dimensional projectivized Lorentz cone. Now, under this transformation, the small group acts as the big group upstairs. So conformal symmetries in the small space are now encoded by the special orthogonal group upstairs. Now, what's called particles in particle physics, the analog in cosmology are fields. So we're going to consider n fields, and each of them has a momentum vector pi and the polarization vector wi. So this, as before, leads to a 2n by 2n gram matrix of rank R, but now the block sizes are always 2. So I'm going to, from now on, in the next 25 minutes, K will always be 2. 2 by 2 blocks. Okay. Now, there are many sources for this. So my friends referred me to this article, right? Spinning conformal correlators. And that was a very useful source. And that's the paper they wrote. Okay, next level, one level up of coordinates, right? So it turns out that in conformal field theory, there is an additional symmetry, and the additional symmetry has to do with the semantics of momentum vectors pi and polarization vectors wi. And the way it works, you also want to have invariance under additive transformation. So if you take the wi and you add a multiple of the pi, then whatever quantity you study should also be invariant. Now, this looks like a harmless operation, but of course, you know that that's an additive group action. That's non-reductive. Okay, this is now a nice additive group action. We're going to be interested in this, but this is now not a reductive group. Well, what are we going to do? We're going to write down some invariant functions. So, well, it turns out that Pij, so this is the dot product between Pi and Pj. Well, that's invariant, right? You do nothing to the p's, right? You just translate the w. So if you dot two p's, they were invariant before, they are invariant now. Hij is this expression. That's also, let me put this down. This is in terms of dot product. So it turns out these Hij's, these are certain 2 by 2 minors of my gram matrix. That's also invariant. And then there's these rational functions, the other 2 by 2 minors divided by some other entry. And here spelled out in terms of dot products. That's also invariant. And the physicists call this the well-known conformally invariant structures. Okay? So these are rational functions either in the coordinates or better in the gram matrix entries, and they are invariant under this additive action. in math language, they generate the field of invariance. The ring, I don't know. It may not be Noetherian, but these are good enough to generate the field of invariance, and this is the third level. Okay, so coordinates, SON invariance, SON plus full conformal group. But now we have these new invariants, these well-known new invariants. So let's try to express our varieties like V2 and R in terms of these, right? So as I said, from now on, K is 2. So for example, let's take N equals 3, R equals 4. So this was one of the matrices, one of the varieties I had, codimension 2, and it becomes very nice. So it turns out I3, 4 in these coordinates is this very, very simple binomial ideal. If you substitute for H and V, these expressions, you clear denominator, you do a little saturation, you get which one? I think it was this one. You get this one. And we're going to get to my favorite component in a moment. So this is in these third level of coordinates. Now, just because I promised that this part is incomprehensible doesn't mean you can't ask questions. So please interrupt me with questions. Well, it's homogeneous with the appropriate grading. So with the way you set up the grading, this has degree 1, 2, 1. So this is graded homogeneous. Yes, Chris. I actually don't know. We decided to ignore this question. The rest was hard enough, but I don't know, actually. That we have a little argument that this generates the field. In the physics literature, all they said, these are the well-known invariants. Okay, well, let's study them, right? So here's for the grad students, okay? Are you clear what we're doing, right? There's somebody out there in cosmology, they study distributions of galaxies and all that, right? And we're going to take their stuff and we're going to turn it into commutative algebra. They will not do it for you. That's what you need to do, right? You need to take their science and turn it into your algebra. That's your task. Okay, so let's do it. So let me write INR for the ideal. So now I make a polynomial ring in variables P, H, and V. So there are this many. So I make a variable Pij, Hij, Vij, K. Type this into Macaulay 2 with the appropriate grading, and I have this many variables. INR is the ideal of relations among these quantities. So let's do another one. So this is again N equals 3, R equals 3. So D, remember D is 2 less than R. So this is, space-time for flatlanders. So this is conformal field theory in a 1 plus 2 dimensional space, but in the embedding space, I go here. Now for the 3 fields, so N is 3, so if I have 3 fields in cosmology, so now my ideal is generated by this expression, and this equals the determinant of the gram matrix. So the determinant of this matrix, which is a polynomial of degree 6 in the xij's, becomes this expression. And it looks inhomogeneous, but it's homogeneous of degree 6. Okay. So the first 2 examples, well, this made us very optimistic. I computed this and said, that's great. Maybe these new coordinates make things easier. Well, nothing could be further from the truth, but at least we got started, right? Yes.
If we said like I don't know, 2, then these the equation that starts with the relation among the Pij, Hij, and whatsoever with corresponding to
Exactly.
the 3 determinants.
No, this 6 by 60 term. This is so R equals 5. Oops. R equals 5 means the 6 rank 5 mate.
If I is 2, then we will find the relation among the minors.
Well, in this example, I'm just looking at the relations among the entries if the matrix has rank 5.
Okay.
Yeah, so all I'm saying here is if you take this red expression and you substitute like this, then the denominators will clear and you get this determinant. Okay. And this made us optimistic. I said, okay, great. Let's look at these matrices and rank conditions, and let's work from now on in the well-known conformal invariant quantities. Okay, structures, they call them structures. Okay. Well, let's first of all maybe talk about the variety walks into the door, right? First of all, what's the dimension? So let me assume that n is at least 3 and r is at least 4. Then the dimension of my new variety, this is now in this, after I mod it out by these conformal, by these additive symmetries. So the dimension is 2r minus 4 times n minus r choose 2. So for example, if r is 5, this is 6n minus 10. And if r is 4, that's 4n minus 6. So it turns out that this is the case, that the cosmology, this was the case they were actually interested in. Okay. Let me explain this. Right? So remember, r is 5, right? So this means their space-time is dimension 3. So what they do, they fix time. So there is a particular time point in time that they fix. It's called the hot Big Bang. Okay. So there's a particular time point where something happened. It was a little bit before and lots afterwards and very, very short. So you fix the time at the hot Big Bang, and you have an emerging three-dimensional space. Okay, that's d equals 3, and therefore r is 5 under the embedding space formalism. This would be the same story for flatlanders, right? So if you have flatlanders at the time of the Big Bang, and then my variety is dimension 4n minus 6, and that's the affine variety. So for example, 4 fields in cosmology, the actual cosmology is r equals 5. So it turns out that ideal I already don't know, right? So I have the ideal I4,5, so I know it contains the 3×3 minors of this 4×3 matrix and a bunch of other things. And we know many, many generators. We don't have the prime ideal yet. Okay. So the previous two were very, very simple, but we tried, using computer algebra. And so this is the first one we don't have generators. So it would be very nice to push this a bit further and see how far we can get. Okay. That's 4 fields in cosmology. So this number here is 14, and the number capital N of variables is 24. Now, in the case of flatlanders, so Big Bang time for flatlanders, we could go a little further. And so this is r equals 4. So there we were able to compute further. And I'd like to tell you, because there were 2 ideas that how this worked. One of them is something called the spinor helicity formalism. Okay. Now, this I had never heard of in my life until a year ago. And it took me quite a long time to figure this out. But now I'm a convert. Okay, it's a very nice way of speaking about several Grassmannians. Okay? Yes, to G to N. Okay, so what you do is you now have 3n vectors. I'm going to parametrize everything in sight by 3n vectors of length 2, and they have these names: US, US bar, and VS. And then I put a long matrix, a 2×3ns matrix, and I look at the 2×2 minors. But I'm using these symbols to denote the minors. So bracket, this bracket ij, then with the bar, the other one, and then there's this ij. Okay. Now you have these funny brackets. You have this bracket and that bracket. And physics, you do bra and cat makes bracket. Okay. Okay, so in my orbit space in these coordinates has this new parametrization. So Pij is this product, Hij is this product. These are Laurent monomials and Plücker coordinates. Okay, so I have now a new parametrization, and these are now Plücker coordinates. All of these brackets are Plücker coordinates, and this is just a quadratic bilinear degree 4, and then there's some Laurent monomial. So now we can compute further, right? So there's the 5,4. This is now 5 fields in r equals 4. There we know the idea, right? So it's minimally generated by quadrics, cubics, quartics, and now there are 50 variables, and we know the dimension and degree. Right? So thanks to this parametrization, we will able. So we couldn't do 4,5, but we could do 5,4 in Macaulay. But it's better, it gets better, namely, okay. before it gets better, let me take you to the fourth level. Okay. Level 1, we have these coordinates of these vectors. Level 2, we have the entries of my matrix. Those are the SON invariants. Third level is these like additive invariants that generate the field, and Chris will figure out the ring generators. Okay. Now, it turns out this is not yet observables. So it turns out what they call the fundamental observables are actually expressed in terms of the well-known conformally invariant structures. And these are the expressions. So the simplest one are these 2-point functions. So the simplest observable is you have you look at galaxies in the sky, and for every pair of galaxies, you measure something. Right? That's a 2-point function. And that's roughly these observables. I'm simplifying. Okay, so this is some quantity. So it's Hij divided by Pij cubed, and it's this expression. And that's the one we really want. This is the one that's a physical observable, and that's the one you want to measure in the sky. Okay. Well, for the students, okay, now what's the first thing you do? Now these people measure stuff in the sky, right? What are we going to do? Right? We're going to take it and we're going to turn it into commutative algebra. And that's, you need to do it, right? They talk about the sky and galaxies. You need to make rings and ideals out of it. So let's do it. So now we have my previous variety, which is V2NR. That's the one we like. And now we're mapping it into the space of observables. So that's now a projective variety, projective space of dimension n choose 2 minus 1. We're going to measure this for any 2. We have n fields. For any 2 fields, we measure this, and we're going to be interested in the relations, the algebraic relations among these quantities, and they cut out some variety. Right? This is a rational map from this affine variety, and we're going to call this the conformal 2-point variety. Okay? By that time, my cosmology friends lost me. Okay? Too much blue stuff. Okay? But we can go, right? Let me call this C2NR. It's a 2-point variety. R is 5 or 4, depending whether you're Flatlander or us. And N is the number of fields you want to measure. Okay, now computing this variety and its ideal is very, very difficult. But based on numerical calculations, so for R equals 5, that's the actual cosmological situation, we believe that the dimension is always 5n minus 11. Of course, it's bounded above by the ambient dimension. Right? This is the expected dimension. This might be doable. Right? This is a conjecture. This just says you write the rank of the Jacobian matrix, and you show that the rank of the Jacobian matrix is what you think it is. Right? And we check this in small cases, but we don't know in general. Right? So dimension is the first thing. But here comes the nice part. So I'm going to call this so this is the last theorem in our paper. Okay, now let's talk about the conformal 2-point variety for R equals 4. So this is Flatlanders at the time of the hot Big Bang. So I have this variety, it lives in this projective space. But now I have the spinor helicity for parametrization. Remember the P's and the H's. So now if I write down the spinor helicity parametrization, I know that the quantity I measure at the 2-point function is this expression, this Plücker coordinate times some other ratio of Plücker coordinates. So these are 2 by 2 minors of some 2 by something matrix. Now, if you see monomials in 2 by 2 minors of a matrix, you think about tropical geometry and phylogenetics, right? And so we use tropical geometry, phylogenetic trees, to prove the dimension. So the dimension of this 2-point variety is 3n minus 7. And so in particular, it has positive codimension for n greater equal 5. So if n is 5, then this is 15 minus 7, that's 8. In a projective space of dimension 9, 10 minus 1, that's a hypersurface. And we know that the hypersurface is a hypersurface of degree 207. Okay, so why? Okay. You have the Grassmannian, G2n. The Grassmannian G2N, we know everything about its tropicalization. Statisticians, your student knows that's the space of trees, right? The space of phylogenetic trees is the tropicalization of G2N. But tropical variety is a shadow of the classical variety. You can compute the dimension, degree, everything you want from the tropical variety. Right? But what are we doing? We're mapping the Grassmannian by a monomial map, right? We have this Grassmannian and we're applying a monomial map into some other space. Monomial maps tropicalize very gracefully, right? A monomial map just becomes multiplication, becomes addition, right? So the tropicalization of this monomial map is a linear map. So what we do is we take the space of trees and we just apply this linear map. The image is a fan, is a polyhedral fan, and you can compute its dimension, its degree, and everything you do in tropical geometry, right? So the upshot here is that thanks to a very clever parametrization that we learned from the physicists called the spinor-helicity parametrization, we were able to then use combinatorial algebraic ideas about 2×n matrices and space of trees to make some progress. We don't have we have a parametrization, but it's ugly, right? So here we have, okay, oops. Yeah, so in general, these things are very difficult and we just don't have nice we have a parametrizations, but they're very complicated. Now you can take these very complicated parameters, you can make numerically Jacobian matrices and compute their ranks Jacobian numerically, but you can't really do the implicitization very nicely. And here we were able to go a little bit further, you know, and then this was sort of nice. We were able to use the combinatorics of phylogenetic trees. I believe there's coffee at 3, so I will absolutely end in time so that we can go to coffee. So what did we do? Let me summarize what happened in this talk. Well, first of all, whatever happened in this talk, it's studied from a conversation with cosmologists, right? So we had our meeting, annual meeting in August. We discussed a lot and we talked to them. In the meantime, there's a lot happening. So many of you have heard about Martina Kubicka, and she studies cosmological polytopes with Daniel Baumann. So there's also lots of interesting things that happen, right? Also on the combinatoric side. What did we end up studying? Then we extracted a math problem, right? And we said, let's actually study symmetric matrices with diagonal 0 blocks. So we looked at these Gram matrices. They had 2×2 blocks along the diagonal. I said, let's forget about everything else. Let's forget about the universe and the hot Big Bang and everything. Let's just look at, you know, symmetric matrices that have 2×2 blocks on the diagonal, and we start computing. Right? That's what we did. We do understand the rank strata now in terms of commutative algebra and algebraic geometry. So this was the first 25 minutes of this talk. Relatively clean results. But then we went further. We sort of were motivated to replace these xij's and so on by more invariant coordinate systems, systems that come closer to what the physicists actually want to measure. And that made things more complicated. But at least we named the disease, again, for the students. So you talk to these scientists, the first thing is you need to define something, give it a name, right? You say, it's the conformal 2-point variety. And they go, what's a variety, right? I mean, but the point is, you know, the point is you just need to define the object. Whether you can compute them, that's another story. Yeah, so these conformal, these varieties that we introduced at the end, they govern the relation on so-called 2-point functions. And it's a very nice story, right? Again, the context is positive geometry, particle physics, and cosmology. And I think there's a lot of good problems that we can move forward. So one of the varieties I like to discuss with my guests tomorrow afternoon is a particular variety for simpler version of a 3-point function. We're going to look at actual 2-point function is a little too easy for them. They want 3-point functions. Okay. Now, often you give these talks, right? You give these talks in, applied algebraic geometry, and then there's always somebody in the audience has to say, is this over the complex numbers or over the real numbers? Right? And really, you want real numbers, right? So there's a more recent paper called kinematic stratification. So if you like real numbers and inequalities, there's a more recent paper. This is Veronica Calvo. She's a PhD student in Leipzig. And Hadley Frost, he's a physicist at Princeton. And there we look at the analog, sort of the inequalities that you have over the real numbers. She's holding the light cone in the hand. So we built this, right? So in Germany, when you go to school for the first time, you get one of these cones. Some of you might know, but you only get one side, and you only get the future, right? So, but in physics, it's very important. There's the past and the future, and you're inside. You're either inside. So the speed limit says you're either inside the past or inside the future, right? And then you have a bunch of particles from the past. They come together at this very singular point. Some scattering happens, and then they go off into the future. Right? That's how it works. And this was also very, very nice collaboration. We were able to reproduce some classical and extend some classical results on physics. And if you didn't pay any attention whatsoever, or you have students at home, try these matrices. Thanks for your attention.